Good morning. It's January 30, CS 747K, a lecture on Hamming code. So, so we have discussed what a parity is, and you are all very aware that even parity means the count of ones should be even, and the odd parity means the count of ones should be odd. So it's simple. So 1, 0, 1, 1. So what's the parity on this? It's odd because if you count the number of ones, those are 3. It's odd. So what's the parity on this one? Yeah, that's simple. So if you know how to find a parity, then this is going to be an easy lecture. Like suppose course outline. So we are right here at the very start. We're just discussing about the basic parity bit protection. So as we discussed, Hamming code or the parity is basically used for protection of our data. So if we gonna lose a bit in our data, we're gonna find using the parity, or if we are going to delete a RAID, I mean a block of RAID, we're going to rebuild the block using these techniques. Okay, so we're just going to discuss Hamming code in this lecture. So that's basic bit parity bit protection. So we are at the very start. Hamming code. So linear error correcting code. So it corrects the error in our code. So parity bits added in line. So we're going to add the parity bits in line. So we're going to have our data bits and we're going to add parity to our data bits. So block code, because it works one block at a time. So it was invented by Richard Hamming in 1950. So he named it Hamming code after his name, his last name Hamming, at Bell's lab, because he was annoyed by punch card readers that kept reporting errors. So they used to have punch card readers, and so if they punch the card wrong, I mean, it used to show errors. So he just want to, yeah, okay, punch the paper. So he was annoyed with the errors reporting due to the wrong punch, I guess. Yep. And he wanted to find some solution for that. So he invented Hamming code to detect the errors, to correct the errors. Hamming is the original published code 7.4. So we have different sizes of Hamming code. So 7.4 is the original published code. So it can detect and correct single bit errors. So if there is one bit flipped in our information, so it's gonna detect and correct one bit. So it can detect 2 bits, but it can't correct that. So it fails to detect triple bit error. So it even can't detect 3 bits. If it's flipped, it won't be detecting the error. If it's gonna flip 2 bits, it's going to detect, but it's not correcting. If there is 1 bit, you know, uh, error, so it's gonna find it and it's gonna correct it. So Hemming 7.4. So encoded message, data bits. So 7 is called encoded message. So we have 7 bits in our message. So we're going to pass 7 bits, and we're going to have 4 bits, 4 data bits. Okay. So number of parity bits, 7 minus 4, it's 3. So we have 4 piece of data and a total of length 7. So 7 minus 4 gonna be 3. So that's how we got. It's not equal to Hamming distance. Okay. So Hamming distance is different from parity, number of parity bits. So it's just a coincidence. It's not like the same formula for calculating Hamming distance. So this is the formula for calculating parity bits. Yeah. So edit distances. So given a set of strings, edit distance is how much change you need to turn one string into another. So we have one string and we want to make that string to a different string. So how many changes we need to turn that? So that's called edit distance. So there are multiple ways to calculate edit distances. So we're going to just discuss a few, and we mainly concentrate on our Hamming distance. So there are various other distances as well. Uh, for example, Lewis-Chain distance, LCS, Lewis, Damuroy elevation, Jarrow distance, and a lot. So only few operations can be performed on each of these edit distances. So for example, Hamming code, we just can substitute. We can't insert, delete, or transpose one string to another. Okay, and this one Levenshtein distance, it can used for substitution, insertion, and deletion, and you can just go through the slides. So Jarrow distance can only transpose. Let's see, let's Hamming distance. So let's see what's Hamming distance. So there is two names here, Caroline and Catherine. So what Hamming distance can do, it can just substitute. Okay, so we'll just substitute. So in place of R, we'll substitute E. In place of O, we'll substitute H. In place of L, we'll substitute R. So we have performed three different operations here. So the Hamming distance is 3. So it can just substitute. It can't insert or delete. And binary. Minimum number of bit flips to change one valid code to another. So for example, 10001, 10011. So what's the Hamming distance between these two strings? 2, 1. Yeah. So there is 1 bit flip changed. The Hamming distance is 1. So it's the same piece of code here. So we're just changing 0 to 1. So 1 bit change. So it's called the Hamming distance is 1. Okay. So in the same way, if we are taking our example, Caroline and Catherine. IN. So we are just changing this one right there. So we're changing R to H, O to R to T, O to H, and L to R. So we are changing 3 bits. We're substituting 3 bits. So Hamming distance is 3. That's it. It's simple. So binary minimum number of bit flips to change one valid code to another. So ASCII value of A, it's right there, 01000001, and lowercase a. So 1 bit flip can change from capital A to small a. Okay. And other codes, LCS, Levenshtein, Jarrow, means insertion, deletions, and transpositions can be done. So LCS of Caroline and Catherine is gonna be 4. So how does that work? So it can do insertion, deletion, and transposition. Okay. Insertion. Yeah. So insertion and deletions. LCS gonna be yes, insertion and deletion. So insertion and deletion. KTH. Caroline. Next one is Catherine. KATHRIN. So it can just do insertions and deletions, no substitutions. So what it's gonna do, Catherine, if we want to change Caroline to Catherine, we'll just we have A's and we have this one, it's same. So we'll just delete and insert and delete, right? So we'll just delete. Yeah. So yeah, we'll just delete O and L and we'll insert T and H right there. So it becomes Catherine. So 2 deletions and 2 insertions, it's gonna be 4. So LCS for Caroline to Catherine is gonna be 4. We'll just delete OL and we'll insert TH. before R. So it's gonna be Catherine. Okay. So LC is gonna be 4. Any questions for edit distances? Hamming distance and error recovery. So an encoding with Hamming distance D can be D minus 1 errors. I mean, Hamming distance D can detect D minus 1 errors, and it can correct D minus 1 divided by 2. Yeah. Right there. Yeah. So D minus 1 by 2 errors. It's a floor division. So if it's going to be 7 by 2, then it's 3. Yeah. So it can correct 3 errors. Yeah. So detect D minus 1 errors and correct D minus 1 by 2 errors. So Hamming distance 1 can detect 0 errors. 1 minus 1 gonna be 0 errors, and it can correct 0 by 2. No, it won't correct any error. Hamming distance 2 can detect D minus 1. 2 minus 1 gonna be. It can detect 1 error and correct 0 errors. 1 by 2. So what's Hamming distance 3 gonna detect? 2, 3 minus 1, 2, and correct 1 error. Okay. Hamming distance 4 can detect 3 and correct 1. Yeah, 3 by 2 is floor division and it's 1. And 5 can detect 4 errors and correct 2 errors. So this is the formula. Just detect D minus 1 errors and correct D minus 1 by 2 errors. Okay. Next, Hamming distance 1. We have just discussed this ASCII example, A to A with 1 flip error. So only a single bit change between two valid symbols. Hamming distance is 1, 3, 1, 0. So ASCII started out as a 7-bit code. Okay. The 8th bit was intended for parity. So we'll just calculate the overall parity. It's 2 ones, so we're just going to add 0 in front for our parity bit, and just see number of ones here. That's 3 ones, so we're going to add 1 at the very front. So the parity bit increase Hamming distance by 1, so it can correct 1 error now, detect 1 error now. So they did not last long. 8 bits extended ASCII showed up in 1978. So what's the use of adding a bit right there? So if one of the bit gonna change here, it's just showing a small, I mean, a lowercase a. So if we add a parity bit in front, and if we change something right there, so we'll get to know like it's a wrong bit changed, right? I mean, if it's 0 and if we're flipping here 1, there is 3 ones and it's showing 0 here. So we'll get to know that one thing is having mistake in here, right? So if we have 1 0 0, yeah, I, well, just
Being able to detect an error but not fix it,
I mean,
that's
yeah,
not helpful.
it's not helpful, but it's in slide. Yeah, okay. So so if this is the code, if something's gonna change here, we can't detect. But if we have a even parity added, like we have 2 ones, we have added 0 because it's an even parity. So if one of the bits gonna flip 1 0 1 0 0 0 1, so this is the message that's transferred. And if we look at here, we have 3 ones, but it's showing 1 parity bit. I mean 0 parity. It's a mistake, so it should have 1. So the error got the message got some error in it, so we can just detect, but we can't say where the error was in this code, right? So that's the use with Hamming distance 2. It can detect, but it can't correct. So this did not last long because yeah, it just can't correct. And now the Hamming distance 3, so it does adding a second parity bit increase. So this is how it is like we'll just write it and we'll just give a parity bits. So what's the parity of 0 and 0? It's gonna be 0 here. 1 0, it's 1. So to make it even, we'll just add 1. So it's 0 here, it's 1 here. So what's gonna be here? 1, and here 1. Yeah. So that's what having distance 3 is. 0 1 0 1 1 1. Yeah. So we need parities on pieces of the data. So break the A into two 4-bit pieces. So arrange in 2 dimensions and make even parity on both the directions. It's having distance 3. Yeah. So if now 1 bit is flipped, it can be correctable. Okay. So let's say we have 0 right there here. So it was changed to 1 now. Let's just change to 1. So what happens? Like, this is the message that was encoded. I mean, that was sent to the transmitter that was received. Okay. So it is odd, and this one is odd, right? It should be 0. So this one is odd. So there is a mistake right there between this column, I mean, this row and this column. So we'll just change it to 0. So that is how it detects one error and corrects the error. So 2 flip bits detectable but corrects wrong. So if we have flipped 2 bits right there, 0 and 1, so it can detect there is some error in here because it's wrong, but it just can't correct it. Okay. Yeah, it corrects wrongly. I'm sorry. Yeah, it's even. So 3 flip bits may be undetectable. It can't detect 3 flip bits. Yep. So having distance 4, we have 6 partial parity bits. Each covers only part of data. So it's the same thing, but we'll add a overall parity right there. So this is gonna be 0, right? It's even ones and it's even ones. So zeros gonna be here. So that's about having distance 4. So let's add an overall parity bits. It's 0. Now having distance is 4. So 3 flip detectable corrects wrong. It can detect 3 flip bits, but it can't correct it correctly. So 2 flip bits detectable, uncorrectable. So 2 bits, 2 bits flipped can be detected, but it can't correct the 2 flip bits. So 1 bit flip remains correctable. So the difference between having distance 3 and 4, it's gonna detect 3 bits, but having distance 3, it can't detect 3 bits. That's the only difference between 3 and 4. So having distance 7 4, also known as 7 4 3. So 7 bits of message, 4 bits of data, 3 bits of parity. So having distance is 3. 7 minus 4, 3. So our 2-dimensional parity bit has 8 data bits and 7 parity bits. It's not very efficient because it's like 1584, a lot of parity bits. Having devised an efficient way to code bits distances 3 and 4 protection with the minimum number of parity bits. Okay, so we're going to see what H74 looks like in the upcoming slides. So other Hamming codes like 844, 743 plus overall parity bit check. So we have 7 bits of data. 1, 2, 3, 4, 5, 6, 7, and we are adding a parity right there. So it means it's 8 bits of data now. Okay, so it's actually 7, but we are adding an overall parity, so it's 8. So 8 4 and 7 4. So that's the difference. It adds a parity bit check. So reliably corrects 1 flip bit, identifies 2 flips, does not correct 2. Okay, that's just discussed. Single error correction, double error correction. Okay, 3 flip bits is detected but may correct wrong. So you can see about all the Hamming 1511, 1611, 128, 120, and so on. So modified Hamming code still used today in many memory chips. So it's still usable. So it's useful to learn Hamming code even today. Key to Hamming code, binary, round numbers. So right there, ones, twos, fours, and eights. So yeah, single flip bits. So decimals 1 to hundreds. So, we will discuss it more clearly. Rounded numbers for parity. Come on. So it's simple. Let's see. So we're talking about 7 bits of data. 1, 2, 3, 4, 5, 6, 7. So these are the bits we're going to pass, and we can detect and correct errors if we have any one bit flipped from 1 to 0. So what happens here? So we have parities with the power of 2's. Okay. So we'll start with P1. Okay, 1 square P2, 2 square P4. Okay, and P4 8, P8 next one. So we have 3 parity bits right here. Okay, and this is 7 bit. So if we add a overall parity bit at the first, so it's gonna be 8 bits. Okay, so P1, P2, P4 in 7-bit data. So in 7-bit data, we have 3 parity bits. So we're going to have 4 data bits. So these are the data bits we want to transfer. So a 7-bit is transferring just 7 digits, 7. So out of 7, we have 4 data bits. Okay, so that's the data we are passing. So we have 3 parity bits right there. So this is how it's all about here what you are seeing. So parity 1, parity 2, parity 4, and this is the message 1, message 2, message 3, and message 4. That's 4 message bits we have. And this is the overall parity we got at the front. If we want, we can add overall parity as well. So that's basically about this slide. So round numbers, powers, decimals 1 to 100,000. Yeah, you can go through this, but this whatever you're seeing here, that just explains the slide. Okay, we have 3 bits of parity and 4 data bits. So how that's gonna explain in the slide. Okay. So a question of direction. Having code was invented in 1950. So before bit orders were established. So in a number, at least significant bit is the rightmost bit. In a string, 0th character is the leftmost bit. Having code is for strings. So strings, so we are just calculating it from left to right. So this is the correct way. We just don't give like right to left. We just don't do P1, P2, P4, and so on. We'll just do it from left to right. Right? We don't do it for numbers. We're doing it for strings. So we are going in left to right direction. Okay. So always remember we're going from left to right, not from right to left. Okay. So when you search for online resources, we have a good online encoders and bad online encoders as well. So just be aware of using be aware of using the good encoders. Okay. So this is the good encoder. It goes from left to right. This is the bad encoder. It's going from right to left. Whereas we're seeing we're doing it for strings. Yeah, we'll bring it up. Yeah.
Yeah, go ahead, bring that up.
So this is a good encoder. So if you go here and encode into 74, giving 4 bits of data, just click on encode, you will get the result right there. 0 1 1 1 1 1 0 0. So if you see the bad encoders part, and let's see.
1100, right?
Yeah, 1100.
Click on the encode right there. Left side. A little bit down, a little bit down, a little bit down.
Oh,
There you go. Encode, decode.
oh yeah.
Your message goes in the space below that.
Oh, that's right. Right there. That's the encoded message it's giving.
And so you see that's different.
Yeah, yeah. These are different encoding messages you can see. So
Yes.
we have one solution for encoding, but
That's actually your storage. it's sometimes more efficient to rearrange bits inside the computer. So what they're actually doing is they're doing the coding that computers will actually do internally to put the bits where it's efficient to find them. That's not the original Hamming code. The original Hamming code is parity 1, parity 2, parity 4, parity 8. They're hard coded into the message, but you can rearrange those. There's all kinds of tricks people can make things go faster.
Yeah.
Stick with the decode one. Stick with the French one. Yeah, it's a .fr on there, the URL, so that means it's France.
French, yeah. So encode with H74. So encode the string 1101. So it's simple. It's code 1101. We know where the data bits are going. Oh, I'm sorry. Yeah. So this is the message we want to code. It's 1101. So we know where the message bits are going. The message bits are going into messages or data bits. So we'll just give 1, 1, 0, 1. So that's the message we have. So this is the message where we want to share, we want to transmit. And these are the parity bits, 3 parity bits we have in our entire message. So how do we get to know about P1, P2, and P4? We know the data. We have the data right there in our question, but we want to find the parity now. So anyone worked with parity bits before? I don't have idea. No. Well, yeah. So parity, just count the ones. I mean, P1. It's simple. Just leave one, D1, D1, D2. I mean, D1, D2, D3, D4, D1 and D4. Okay. And parity 2, it's gonna take 2. Okay. Now P2, D1, leave 2, and D3 and D4. Now parity 4, it's gonna take all the 4 at the end. P4, D2, D3, D4. Okay. So how do we calculate these parities? So our aim is to calculate the P1, P2, and P4. So let's take P1. What's D1? 1. D2 is 1. D4 is 1. So to make this one even parity, we need to add 1 to P1, right? So P1 is gonna be 1. Sorry, P1, 1. So about P2, we have P2. What's D1? It's 1. D3, it's 0. D4, it's 1. So how to make it even parity? What's P2? Is 0, yeah. So P2 is going to be 0. And now P4. P4, D2, D3, D4. So P4, D2, D3, D4. 1, 0, 1. So what's P4? 0. So this is the encoding method we use for Hamming code. Yeah. So it's simple. You need to know what are parity bits, what are data bits. Just substitute your data into data bits and make every parity even. That's it. So right here. So if we take our binary table 0 0 0 1 1 0 1 1 0 0 0 1. It's from 0 to 7. So how's it like? What's the parity 1 is doing? It's taking these values 1 3 5 7. That's what we have done it 1 3 5 7. Yeah. So about P2 is the second ones. Yeah. So it's taking 2 3 6 7. So we have just took 2, 3, 6, 7 bits here. And what's this one doing? Parity 4. It's right there. So we have taken these 4. So that's how we got this one. So a simple trick is just for 1, just take 1, leave 1, take 1, leave 1, take 1. And for 2, just take 2, leave 2, take 2. And for 4, just take all the 4 from here. Yeah, it's easy. So that's what this slide explained. Any question here from the slide now? So this is the encoding with H74. Let's say encoded string 1101. Step 2, pad with parity placeholders. So P1, P2, P4, 1101. That's what we have done in our very first step. Then some odd bits to calculate P1. So P1, 1, 1, 1. So P1 should be 1 to make it even parity. So P1 is 1. So and P2, 1. Then just leave these two 0, 1. P2, 1, 0, 1. So P2 plus 1 plus 0 plus 1 to make it even. So P2 should be 0 and P4 should be 0. That's what we have done just now. So encode 84. So it's the same thing, just add one parity bit at the very start. So just calculate the oral parity and do the thing. Like we have right there the final 1, 0, 1, 0, 1, 0, 1. So that's the encoded part we have. Yeah, that's the encoded part we have. So that's a 7-bit string. 1, 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7. So to make it 8-bit parity, we just add a parity bit at the very first P0. So what it does is calculate the overall parity. So what should be P0 here? 0, yeah. So that's an 8-bit Hamming code. That's it. That's what the next slide explains us. 8-4. Yeah, so start with 7-4 and code string some all bits and calculate P0, 0 parity. I mean, first parity. It's done. Okay. We added one more bit, so that's why it became 8-bit. So decoding a message. So how to decode a message? So it's
Next one.
yeah.
Got the error, yeah.
Yeah. So it's just the reverse process of what we have done. We just encoded it. So just do the reverse part. It's decoding. So just note all the P1, P2, P3 bits and check what got the error. And yeah, that's it. It's easy. So we'll first check whether the parities are correct or not. I mean, we'll just check the message was sent correctly or not. If it's sent, then we'll just strip the parity codes and we'll get the message. So decoding 1511 with the error. So we have an error right there. We know that, but suppose let's say we have got a message and we need to decode that message. We don't know if that have an error or not. Okay. So 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0.
Oh, P0.
Yeah, no P0. Okay. So what's the parities we have here? P1, P2, P4, 5, 6, 7, P8. So we have P1, P2, P4, and P8 parities. So it's just the reverse part of decoding, encoding. We'll just decode it. Yeah. So it's D1, let's say D2, D3, D4, sorry, D4, D5, 6, 7, 8, 9, 10, 11. Okay. So let's take P1. So what we have P1, D1, D2, D4, D5, D7, D9, D11. Okay. And we have P2, D1, D3, D4, D6, D7, D10, D11. Next we have P4, D2, D3, D4. Yeah. And D8, D9, D10, D11. Any questions till now? We have P8. So it's gonna be 8. P8, D5, D6, D7, D8, D9, D10, D11. Okay. So that's what we have just discussed before this slide during encoding, how to get the parity bits and the data bits together right there. Okay. So we'll just write all the values. It's P1 0. Let's write all the values. D1 1. What's D2 0? D4 1. D5 0. D7 0. D9 1 and D11 0. So this is the parity bit. So did we get anything wrong in this? I mean, there are 3 ones and our parity is 0. So we have an error in here, right? I mean, this should be either 1 or there should be a bit flip changed in the code, right? So there is an error here. We can say that there is an error in this bit. Okay. Now let's go to P2. P2, D1, D3. P2 is 1, D1 and D3. D1 is 1, D3 is 1. D4, D6, D7. D4 is 1, D6, D7, 1, 0. D10, D11, 1, 0. Okay. So this is the parity. So do we have any error in this thing right there? So 1, 2, 3, 4, 5 ones, and we have 1 right there. So it's 6. So it's even, right? So there is no error right there. Okay. And let's just do this thing. P4, D2, D3, D4, D8, D9, D10, D11. And again, do we have any error in here? Yes, right. So there is that's not an even parity. So that should be 0 or either one of the bit was flipped right here. So there is an error here. In what? P4 got error, P1 got error. Now let's see P8. It's 1 0 1 0 0 1 1 0. Do you have error in here? No, that's even parity, so no error. So this was correct. So we got error in P1 and P4. Okay. So error in first parity and error in fourth parity. So first parity plus fourth parity. So that's going to be 5. So just count fifth digit and change flip the digit. Okay. 1, 2, 3, 4, 5. So let's change 0 to 1, and that's the message that was encoded before. So that's the error we got. Okay. So that's how we detect and correct our error in 7.4. It's not 7.4, 15, 15, 15, 1511. Yep, that's a 1511. Yeah. So that's how we got the message. We saw whether the message has an error or not, and we just corrected the error as well. Okay. So any questions from this one? You know? Yeah. So let's see. So this is the slide. We just done that. We just flipped 1 to 0. We just corrected it from 0 to 1 right there. So that's what it was flipped. It's now check once. That's what we have done. Once odd problem, even okay, odd again problem, even okay. So we just summed up both those and get 5 and just flip the fifth digit. That's it. It's simple. And 1611, that's the thing. So 1611 even parity. So we are going to add a parity bit at the very first, and let's see whether it's 2-bit flip is even. Okay, check once, two. So there is 2 bits flips. So a p. So this is how it worked. Checking once, even, even, odd, even. So odd. So fourth bit was flipped. So in general, we'll think like this was flipped P4, right? So we'll just do what 1, 2, 3, 4, and we'll just flip 1 to 0. But instead, we have a overall parity check bit. So this gives us it. What if there was no P naught? We would think P4 itself was flipped. Okay. So P naught P4 mismatch indicates a 2-bit flip. Okay. So if we are correcting right there, if we are correcting it, we'll have a 0 here, so it will be mismatched. So now we get to know that it's not a flipped bit, so we can detect 2 errors. We can't correct, but we can know it was 2 flip bits. Okay.
P0 did tell you that there were an even or odd number of bits. Overall parity of the message is odd. That tells you there was 1, 3, 5 bits flipped. The overall parity of the message comes in good. It tells you there were 0, 2, 4, 6. So when you get 1 bit indicating it's wrong, but P0 indicates no errors, that tells you there was actually 2 flips. Once you say that on the microphone,
Oh,
whatever.
that's fine. So that that's the thing they'll get to know in this slide. And Phil Hamming code H7484 code 4 data bits notices 8 2 times 3 power 3 11 data bits. Yeah, in general. So this is what we have all discussed till now. 74 and 84 4 data bits. We'll just have one parity bit added to 7 bits. It's gonna be 84. So 7 minus 4, 3 dat. Sorry, 4 data bits and 3 parity bits. 7 minus 4, 3. So same case for everything. So partial Hamming code 2p minus 1 less than n less than 2p encodes 2p some check. So this gonna be more in depth. So it's out of scope for this class at least. So if you are interested, you can just go and dig what was there in there. So 62, 64, 72 minus 64, 7 plus 1. So p naught check bit included. So whether the parity bit was included or not with the given numbers, you can just check that. So we'll fully specified Hamming code 72, 64, 4, 72 bits in coded message, 64 bits raw message. We're just sending 64 bits of message and we have 72 bits of encoded message. Hamming distance is 4 plus overall check bits exist. So 71, 64, 3, 71 bits of coded message, 64 raw messages, Hamming distance 3 implies no check bit exists. And yep. So decoding exercise, it's 12.8. If you are interested, you can just go ahead and do that. Like, and this is the encoded message, 12 bits long. You can just decode the message now if you are interested to do, or we could do it on slides. P naught check bit. If there is a P naught check bit or yes or no, we'll just check no check bit. We'll just take ones 1 1 1 1 1 0 0. It's even, so there is no mistake in ones. Twos 0 1 1 1 and 1 0. That's it. So it's even, so no mistake in here. Fours 1 1 1 1 and 0. It's even, so there is no mistake in there. Eights 1 0 1 0 0. So even number of ones, so no mistake. So strip the parities and you'll get the message we have sent. And this is another exercise. So do you want to try? Encoded message 000011101010. So if someone wants to try, you can try, or someone wants to do it on board, you can do that as well. Someone's interested. It's easy. Is there's
Something,
yeah.
so go ahead and bounce through it.
Yeah.
We'll give you a homework assignment
Yeah.
to do that. Yes.
Decoding exercise 2 details. So this is the message we got. Chicks 001111. So even number of ones, so no mistake. And again twos, even number of ones, no. There are odd number of ones. So there is a mistake in check bit 2. So P2 got mistake. So it's odd, so error. And check force 01110. So there is odd number of ones. It's not even parity. So there is a mistake in 4 as well. So it got error in force. And next check 8s 01010. There is two number of ones are 2, so it's even, so there is no mistake in there. So find column error 2 plus 4. There are error in 2 and error in 4. 4 plus 2 gonna be 6. So just flip the 6 and you will get the message. Decoding exercise 3, that's the same thing. Ones, twos, fours, eights. Find column with error. Yep. Yeah. So error is the same twos parity. So any questions in this slide? We have discussed a lot of problems till now, so I think there should be no questions. So just count the number of ones. If it's odd, then there is a problem in that. If it's even, so there is no error message. Just count it, so and add at the end. So whatever the parity bits you got in error, so just add it and just flip the bit, and that's simple. So having code YouTube. So we have some YouTube videos as well. You can just go in there, and there is no good YouTube videos as well for having code. So this video, it was having music, and there is no one explained. It's just showing, like, writing the bits and showing it, and they just taken out this one. Yeah, they have deleted this. Yeah, this one is from someone explaining this second one, but they've taken it out. So that's the end of this. Yep. So that's it for today's class. That's the Hamming code. And let me stop recording. Any questions? Any feedback? No?